Hello everybody. In this video we are going to discuss a method to tune your PID controller in the frequency domain, and that is what we call loop shaping. So what is loop shaping all about? So what is the definition? Suppose we have a system or a plant or a process, HP, and we want to control that system, HP, by means of a controller, HR. So what we are going to do is we are going to examine the open loop, so HR times HP, and we're going to modify the controller in a way to modify that open loop. And the goal is, of course, we want to meet the control system requirements, both on performance but also with respect to stability. And that is an iterative process. And in the end, we have a tuned method, a tuned controller, and then we say the loop is shaped. So how does it work? Let's start with an example as depicted over here. And in this example, I have a motor over here, and that motor has an inertia J1, and we are going to measure the position of that rotor, and that is called V1. And to that motor, we apply torque T. And connected to the motor is a load, an inertia J2. And between the motor and inertia is a kind of a flexibility, which can be defined by a torsion stiffness K and a torsion damping D. Well, this is a practical setup of this example. Here we see the motor with the encoder, and that is providing that feedback V1, and we have that flexibility over here towards the load over there. So this is our system, and based on that system we can start off with modeling. So what we're going to do, we are going to define two free body diagrams, both for this inertia and one for that inertia. So this is my setup, this is my system, my model, in which this is my inertia of the motor, and we're going to measure that position V1, and we have an applied torque T over here. And by means of that torsion stiffness K and torsion damping D, the load is connected to that motor. And based on two free body diagrams, one on this body, so this inertia, and one on that inertia, we get two equations of motions. And when we substitute these equations of motion into each other, we get a transfer function with V1, the position of the rotor, as an output, and the torque T applied to the motor as an input. And then we get this transfer function. V1 over T equals 1 over the total inertia times S squared times this complete fraction, and this fraction is S squared times J2 over K. J2 is the load over here, plus D over K times S, damping divided by the stiffness times S plus 1. And in the denominator we have a similar expression, but we have J star over here. And J star is an equivalent inertia, which is equal to J1 times J2 divided by J1 plus J2. So what do we see over here? Well, we have the low frequency behavior over here, which equals J, the total inertia, times S squared. So it's a part in the Bode plot which will decrease by minus 40 dBs per decade. And then we have a numerator over here, and that numerator has its lowest value at a anti-resonance frequency, which is equal to the square root of K over J2. And we have an expression here in the denominator, and this expression is at the lowest value at a frequency, an angular frequency, which is equal to the square root of K over J star. So when this is at the lowest, we have a peak in the frequency domain, which we call the resonance frequency. And when this is at the lowest, we have a dip in the frequency characteristic, which we call the anti-resonance frequency. So let's make a Bode plot out of it, and I've done that over here. And the dashed line is the theoretical Bode plot of that transfer function which I showed previously and which is also depicted over here. And I also did some FRF measurements to that system, and here we have the measured Bode plot using these numbers, and we see that the measured Bode plot and the Bode plot coming from this model are yeah, just as equal to each other as we expected. And this is my phase diagram. And what we see is that we have over here my anti-resonance frequency, which is almost at 19 Hertz in this situation. And I have my resonance frequency over here, which is at 27 Hertz. And in between, we call that the crossover frequency. We see that the phase has its largest value, and that is over here. So we have a positive phase shift, which occurs at this crossover frequency. Well, let's use this characteristic to define the way in which we're going to tune this controller. So first of all, we define that crossover frequency exactly in the middle of that anti-resonance frequency at 19 Hertz here and the resonance frequency at 27 Hertz. So I defined my crossover frequency at 23 Hertz, exactly in the middle. Suppose in my first example, when we don't use that method of loop shaping, and suppose we only wanted to use a peak controller, and we defined the 0 dB point exactly at that crossover frequency. So we want to have an amplitude of 1, which equals 0 dB at a KR in this example, which is 32. This is also known as the bandwidth, the open loop bandwidth of my system. Suppose we want to have that 0 dB at that crossover frequency. Well, this is then what we see. There are a couple of measurement plots in this figure. This is my root locus, which we are not going to use in the discussion of this example, and this is my closed loop behavior. The most interesting part of this figure is my open loop behavior, because that is defining my stability. And what we see over here is that we have a really low phase margin of only 2.2 degrees, which is really, really low. So that is bad for stability. And that is also what we see in the Nyquist loop, because that Nyquist loop over here is very close to the point -1. So we have almost no phase margin left, which is not good for stability. And that can be seen in both the sensitivity plot, but also in the time domain. When we look to the sensitivity plot, we see huge peaks over here. And when we have a peak which is higher than 0 dB, then my controller functions worse. So I have a worse functioning controller with respect to a system which has no controller at all. So this is really worse. And also in my time domain, in my step response, I see a lot of ringing over here, and almost at 2.5 seconds, we see that we have a settled system. So the system is ringing and it's really slow, and we have a very poor phase margin. So it's really a bad result. So we want to use loop shaping. So what is the proposal, or what is the approach which we are going to use? Well, we start off with defining that crossover frequency as discussed between the anti-resonance and resonance frequency. We call that omega CO, the crossover frequency. When we have that, then we define a peak controller with a lead filter. So a lead filter is a tame decontroller, and from that lead filter we define a 0 at a crossover frequency divided by 3, and we define the pole of that lead filter at a frequency which is equal to the crossover frequency times 3. So we can also say that tau d of my lead filter is equal to 3 over omega crossover, and we have a tameness factor b of 1/9. And when we have done that, we increase the gain by increasing the p action of my controller in a way that we have at the crossover frequency an amplitude of 1, or an open loop amplitude which is equal to 0 dB. And then we are ready. But suppose you want to have an integrator in your system, because you have, for instance, reasons to have a really zero steady state end fault, so an end error which is really going to 0. Then you have to apply an integrator, and when you want to do that, define the 0 of your integrator at omega crossover divided by 5. So the tau I is equal to 5 over the crossover frequency omega CO. And when you have a lot of noise in your system, you could for instance, use a second order low pass filter, and then a good starting rule could be that you set the natural frequency of that second order low pass filter at omega crossover times 6 and use a damping ratio, so a beta of 0.6 as a starting value. So then you judge your performance in the time domain, and you judge your stability margins in the frequency domain, and then you could readjust the parameters because it's an iterative process, but it's really good starting value. So this is the loop shaping procedure, and point 1, 2, and 3 are the basic elements of it. So let's do it in that example which we discussed earlier. So step number 1 is we add the lead filter with the P action. So we had a crossover frequency at 23 Hz, which equals 144.5 radians per second. Now we are defining our lead filter, and the transfer function of a lead filter is equal to H is 1 or 1 plus tau d times S over 1 plus B times tau d times S. So we have a 0 over here and we have a pole over here. And this is another way of writing that transfer function in a way to make it easier to implement in the frequency domain. So we put the 0 as omega crossover over 3, and that equals 1 over tau d, so we can say tau d is 3 over omega crossover. And in this case, it's 3 over the crossover frequency in radians per second, so 3 over 144.5, so my tau d is 0.021 seconds or 21 milliseconds. We can do the same with the pole. We said we define it as 3 times omega crossover equals 1 over b times tau d. So this is the pole of my system. So b times tau d is 1 over 3 times the crossover frequency in radians per second. And then we get a pole, a time constant in the denominator, which is equal to 2.3 milliseconds, 2.3 milliseconds. And what you also see is when you divide this by that value, then we see that we have that tameness factor B of 1 over 9. So now we have defined the lead filter by applying the rules of the lead filter, and now increase the P action in a way that at that crossover frequency over here, that my amplitude is 0 dB, or I have an open loop amplitude which is equal to 1. And in this case, we can do that by increasing the P action to 10. So now we have our starting value for the lead filter with P action using the loop shaping rules. Now, this is what happens, and this is the most interesting thing, because this is my open loop behavior. So this is the Bode plot of my open loop behavior, and you see over here that we have a very good phase margin. It's 52 degrees, and remember, with only using a P action, we started off with 2.2 degrees. So this is really good. And we see that when we look to the Nyquist plot, well, this is my Nyquist plot, and we have that phase margin over here, which is these 52.2 degrees. So it's a really good phase margin. So we are way off with my Nyquist plot compared to the -1 point over here. When we look to the sensitivity, we also see a really nice sensitivity plot. So it's a nice suppression over here, but compared to only the P action, we don't have that overshoot over here. So we have a couple of dBs left in the right part. So after the omega crossover in that sensitivity plot. So good suppression, but also very low peak values over here. And that all is also visible in the time domain. When we look to the performance over here, to the step response, we see it's a really good step response. It has a low overshoot in the time domain over here. And what we see is the system is settled somewhere over here. And remember, it was 2.5 seconds when we used a peak action only. So we have a very good result. We have a phase margin which says everything about stability of 52.2 degrees and a really low settling time of only 0.11 seconds. So that is really good result. So your procedure could end here. But when you want to use a PI filter, because you have requirements which make adding a PI filter necessary, then you should define your PI filter, of course, your e-controller, of which its transfer function is equal in the standard form like this, 1 plus s times tau I divided by s times tau I. And we've seen that we can, using the rules of loop shaping, we can define tau I as 5 over the crossover frequency omega CO, and then we get 0.0346 seconds. So it's 34.6 milliseconds. That's the time constant of my PI controller. So when we add that, this is my open loop response, and we see, of course, by adding that PI controller that the phase margin drops, because an integrator is not good for stability, but it's really good for suppression values and for low frequencies. So what also happens, we can see it over here in that Nyquist plot, we see that that phase margin has lowered with respect to only the P controller with that lead filter, which we discussed previously. When we look to the sensitivity plot, we see that the sensitivity shows a really good suppression and low frequency because of that implemented integrator. We see, for instance, over here, when we have that frequency of 10 to the power minus 4 kilohertz, that my suppression is, well, let's say minus 120 dB. And when we went back to that lead filter, we saw that the suppression was only minus 80 dB at that same frequency. So adding that adding that PI filter really gets a good low frequency suppression over here. But of course, here I have some more, let's call it so-called overshoot in the frequency domain. So my sensitive is worse over here. And we see it also, that behavior back. We see it in the time domain. When we look to the step response over here, we see somewhat more overshoot and we see somewhat more ringing. So the settling time has increased with respect to only the P filter and the lead filter. So my final result over here is a phase margin of 34.4 degrees, settling time which has been increased to 0.23 seconds, but of course a low frequency suppression over here, which could be very good for reasons why you implemented that PI filter. Suppose that you also wanted to design a low pass filter because your system is noisy. Well, then you could use the general transfer function of a second order low pass filter, which is equal to omega 0 squared divided by s squared plus 2 times beta times omega 0 times s plus omega 0 squared. Well, we have said that the omega 0 put that to 6 times the crossover frequency, so 6 times 144.5 radians per second in this example, which equals 867 radians per second. And you use a beta value of 0.6. And when you do that, this is my open loop response again. You see that the phase margin somewhat lowered over here. So again, low pass filtering also yields a somewhat lower stability, which we see by that phase margin. And what you also see is, because we have a second order filter over here, I have a maximum phase drop of minus 360 degrees over here. Well, also Nyquist plot shows a somewhat worse phase margin over here, and we see that the sensitivity plot over here shows same low pass behavior because nothing changed in the low frequency behavior because we have implemented that PI filter. And here it has become somewhat worse. And also in the time domain, the step response, we see that, well, the system shows more ringing than before. So the phase margin dropped a little bit to 22.6 degrees, which is not that good in the end. So we have to look into that, and we have a somewhat higher settling time. So the final result, when we put it all together, and I plotted it, all these results in one plot, you see the effect of a implemented lead filter and what it does and the low frequency behavior with respect to implementing the PI controller. This is the closed loop behavior, not that interesting, but this is a really nice plot, which is the Nyquist plot, which is another way of looking to this Bode plot, of course, Nyquist plot of my open loop. Well, we started off with the blue curve over here, which was only the P controller with a very small phase margin. Then we went to the lead filter and the P controller, which is the red Nyquist plot over here, with a very good phase margin. And when we add the PI controller, well, the phase margin drops, which is yeah, let's call it the yellow one, and the purple one shows the Nyquist plot when we also implemented the low pass filter. So we see that the phase margin drops when implementing a PI controller and when you also implement that low pass filter. And this is my sensitivity curve. Well, only a P controller is a really bad idea. So we see that over here. So we start off with the P controller with the lead filter. That is the red curve over here. It's a really smooth one. And when, of course, you implement a PI controller, you get that very good suppression over here, but it costs somewhat more increased yeah, sensitivity magnitude and the parts of my frequency plot after the crossover frequency. So, summary, by using this example, we have seen that using a lead filter is really important because it increases the system's stability. The phase margin increases. That is very important. Um, implementing a PI filter, by implementing that, it decreases sensitivity for low frequencies. That is what it does. That is why you want to implement a PI filter, so an integrated in your controller, but it costs phase margin, so it's worse for stability. And of course, an extra low pass filter may avoid amplifying measurement noise. And of course, it also has a somewhat more worse uh, aspect with respect to stability, as we have seen. So conclusions with respect to loop shaping, we are using it very much in motion control. So when you are planning to define a controller and a motion control application, it's a really good way of tuning your controller. And we have looked in a way in a loop shaping procedure with feedback from the motor controller. Um, of course, for performance, use feed forwards. It's always good to have a really good performance. So, yeah, I would say there's no excuse for not using feed forwards. Do it. Then you design your controller and the frequency domain, and you judge it by looking to the bandwidth, the omega crossover, the phase margin, the gain margin, and your sensitivity. And of course, don't forget judging your performance in the time domain, because that is why you are implementing a controller. Judge it by looking to the settling time, your tracking behavior, noise suppression, etc. Well, that's all about loop shaping. I thank you for watching, and I see you next time.